And welcome again. This is Paul Walcher. Today, in this lesson, we're going to talk about 4.5, which is honestly one of the bigger sections of Chapter 4. In 4.5, we're going to start solving equations that have logarithmic pieces and exponential pieces. Now that we've got this new notation, we need to talk about how it affects equations. So, not going to spend a lot of time in PowerPoint today. The main things you'll need to know for this section all come from previous sections. These are just the properties of logarithms over again. We had these in the last video. These two are the cancellation properties. We'll use these quite a bit. Then we've got the product rule, quotient rule, and power rule. We'll use those quite a bit. Change of base formula, not as much. It just depends on how we solve, whether we'll need to use this at all. And we might have to use it for some simplification. Just depends. Then, the only really two new bits of theory we'll be using is this information. It's just two new solving principles. So A equals B, if and only if, can do two new things. You can raise both sides into the exponent of the same base. So for example, if I had A equal B, I could say 3 to the A equals 3 to the B. I could say 7.5 to the A equals 7.5 to the B. More importantly, I could also, if I had like 3 to the X equals 3 to the 7, I could drop from there, from this form, back to A equals B, so back to X equals 7. That's actually a rudimentary way of solving an exponential equation. To do that, you have to have the same base, so it's not that helpful, but it's still something you can do. Similarly, you can also take the logarithm of both sides. You can take a logarithm base c of both sides, so if I had A equals B, I could take a log base 4 of both sides. Or an ln, a log base e. Or a log base 10, or a log base 3, or a log base 7. Point is, this is a new operation we can do to both sides of the equation, just like this is. You can put both sides into the exponent of any base you choose, as long as it's the same one on both sides. You can also take a logarithm of both sides. And like I say here, 1 we're generally going to use when we're solving logarithmic equations. 2 we're generally going to use when we're solving exponentials. And that's really all the theory we're going to be using for this section. So, let's start doing some exercises. We're going to start by solving exponential equations. And we're going to start with exercise 7 from 4.5. Here we have 3 to the 2x minus 8 equal 3 to the 5x plus 1. Now this is a very simple case because if you have the same base on both sides, we actually saw from property 1 that you could just jump down straight to 2x minus 8 equal 5x plus 1. So if you have the same base on both sides, you can basically just drop it. And then we can solve this. Add the 8 to both sides. Subtract the 5x from both sides. Have negative 3x equal 9. So x equals, let's see, divide by negative 3. And you can check it just like before. Just plug it in the original. Check. 3 to the 2 times negative 3 minus 8. 3 to 5. I guess I should put a question mark in there because I don't know whether they're equal or not. 5 times negative 3 plus 1. Alright, that is 3 to the negative 6 minus 8, so that's negative 14. Equal 3 to the negative 15 plus 1, that's also negative 14. So yeah, they're equal at that one. So that is its solution. And in general, if you've got both sides can be powers of the same thing, you can just do it this way. It's somewhat rare, but I'll give you another example. This one's just one I made up. So if you got like 8 to the 3x minus 2 equal 4 to the 5x plus 8, well, they're both powers of 2. See, this is 2 to the third to the 3x minus 2, and that's 2 to the 2 to the 5x plus 8. And then if you remember your rules of exponents, if you raise something to an exponent and then raise that to an exponent, you just multiply the exponents. So this would be 2 to the 3 times 3x is 9x. 3 times negative 2 would be 6. And then on the other side, I would have 2 to the 2 times 5x is 10x. 2 times 8 is 16. And then you just set both sides equal. So you get 9x minus 6 equals 10x plus 16. Then you'd add the 6 to both sides. Subtract the 10x. Get negative x equal 22. So x equals negative 22. This process we've been doing is really just the shortcut. It only works if you have the same base on both sides. So what if you can't get them to the same base? So let's take, I'm just going to make another one up. This is going to be the first full problem. So this is the one you really should pay attention to. 2 to the, well, let's say 7x minus 1 equals 3 to the 4x minus 2. Alright, you got that? Now, can't get these to the same base. They are not powers of the same thing. So what do? Well, we're going to make use of two properties. I hope you kept your list of properties and solving principles close. We're going to make use of the power rule for logarithms, which if I have a log of both sides, I can take the power out of the exponent and bring it out front as a coefficient. But I have to have a logarithm of both sides. But that's no problem, because remember the second solving principle said we could take a logarithm of both sides, any base we choose. So what base are we going to choose? Well, I usually do base E or base 10, just since those are easy buttons on the calculator. But if you want to take another base, that's okay. And we'll do that later. I'll probably do this problem a second time using a different base. But for right now, let's just use a base E. I use base E logs just because, remember, base E logs are ln, and ln is shorter to write than log, or log base 4, or log base 3. So I just tend to write this for shorter amounts of writing. So I'm going to take an ln of both sides. Log base E of both sides. ln of 2 to the 7x minus 1 equals ln of 3 to the 4x minus 2. And what does that get us? Well, now we can use the power rule for logarithms. which says I can take these powers and bring them down out front. So now I'm going to have 7x minus 1 times ln of 2 equals 4x minus 2 ln of 3. And that may look nasty, and in fact our work for this is going to look a bit nasty. But realize here we've just got a number times a parentheses and a number times a parentheses. This is just a linear equation. So now all I have to do to solve this is solve it like a linear equation. In linear equations you simplify, you remove parentheses, then you get all your variable terms on one side, then you divide out the coefficients on the variable. And that's it. So multiply the ln of 2 through to remove the parentheses, 7x ln of 2 minus ln of 2 equals 4x ln of 3 minus 2 ln of 3. You notice why I prefer something that has me draw less symbols. Ln is shorter than log, and it means I have to, in the long run, I have to draw a lot less just because I'm having to draw ln so many times. It doesn't save you. It probably doesn't save you that much time, but it feels like it. So now I can take all my x terms on one side, so I'll move this one over. And I will add this one to the other side. So after we do that, we will now have 7x ln of 2 minus 4x ln of 3 equals ln of 2 minus 2 ln of 3. I can factor out an x on this side. X times 7 ln of 2 minus 4 ln of 3 equals ln of 2 minus 2 ln of 3. And then divide out the parentheses. X equals ln of 2, and I had to redraw this, but you can see we're back to basically the exact same place we were. So for the last step, just divide out your coefficient on the x here, 7 ln of 2 minus 4 ln of 3. And we're done. X equals ln of 2 minus 2 ln of 3. All of that over 7 ln of 2 minus 4 ln of 3. That is the exact answer. A lot of times in the homework or the book, they might want you to approximate this answer, because honestly there's a lot of ways you could write this. I picked ln as just an arbitrary log base of both sides, but you could have used any log base. So I could have used log base 2, log base 7, log base 10, and the only difference really would just be the log I had in front of all the numbers. So I could have had a log base 8 of 2 minus 2 log base 8 of 3 over 7 log base 8 of 2 minus 4 log base 8 of 3. The exact same answer. So it doesn't really matter which logarithm you choose. in any case, you might have to approximate at the end, and in that, if so, it's probably easier to pick a log that you already have as just a button on the calculator, rather than having to menu surf to get log base 8 from the math menu, or worse, use the change of base formula in every case. So let's actually look at what this would be in the calculator. So we have our calculator up here. Let's take a look. We have ln of 2 minus 2 ln of 3. So parentheses, ln of 2 minus 2 ln of 3. And then we divide by 7 ln of 2 minus 4 ln of 3. Divided by 7 ln of 2 minus 4 ln of 3. So an approximate answer for that is about negative 3.287. However many decimals they want you to round to, they will tell you in the problem. Approximately negative 3.287. So another way of approaching this. Some of my students really prefer this. If you take a log base that specifically corresponds to one of these bases. So say I took a log base 2 or a log base 3. So if I took a log base 2 of the left a log base 2 of the right, well, you get the nice property of, on the left, log base a of a to the x is just x, so the left side is just going to be 7x minus 1 equals, then the right side, well, you are just going to have to do the same thing on the right side. Log base 2 of 3. Now, this one you just have to deal with less logs. I mean, on the left side you still got the 7x minus 1. On the right side you'll have 4x log base 2 of 3 minus 2 log base 2 of 3. And just like last time, you get all your x terms on the same side, so 7x minus 4x log base 2 3 equals 1 minus 2 log base 2 of 3. Factor out the x. And divide out. 1 minus 2 log base 2 of 3 over 7 minus 4 log base 2 of 3. Now, that is actually the same thing as this. If you'd have to either use change of base formula or the log base function in the math menu to plug that in. It's kind of 6 of one, half dozen of the other. You're going to be spending about the same amount of time calculating an approximation with this that you'd save in doing this. So it really just depends on which one you prefer. I generally just do this, but you're welcome to use whatever method you want. The actual simplest way of writing this is just to use some log properties to simplify the top and simplify the bottom. So, the top would be, this is completely optional. You don't need to do this at all. But once you get an exact answer, you're done. But you can take that 2 into the exponent, so that would be ln of 9. Then you can make that 7 into the exponent, so that would be ln of 2 to the 7th would actually be 128. And then 3 to the 4th would be 81. And then that would be ln of 2/9 by the quotient rule, and the bottom would be ln of 128 over 81. And then that, I can use the change of base rule to write as the log base 128 over 81 of 2/9. So that's probably the shortest way of writing the answer. Now, is it the best way? Not necessarily. You might rather have it in LNs or something else, but that's probably the shortest way. So let's do a simpler problem. This is exercise 30. Do 4 plus 3 to the 5x equal 8. First off, you solve for your exponential piece. So move the 4 over, you get 3 to the 5x equal 4. Then you want to get the x out of the exponent, so you take a log of both sides. I'm just going to take an ln of both sides because that's my custom. But you can take any log you want. Then power rule lets you bring down the 5x. Let's go to a clear background. And then x equals, you divide both sides by 5 ln of 3, ln of 4 over 5 ln of 3. Not that bad if you know what you're doing. Just get your exponential piece alone on its side, take a log of both sides, use the power rule to bring the exponent down, then divide. Let's see about 41. This is a problem that mixes a couple things. 41, I have x squared. All of these, I haven't actually been writing the instruction, but the instruction is just solve the equation. So I have x squared times 2 to the x minus 2 to the x equals 0. Well, this mixes several pieces, but the thing is I can still use my previous knowledge. I know I can factor something like this. It has a common 2 to the x. If I factor out 2 to the x, I get x squared minus 1 equals 0. So, according to my solving by factoring, I have to have 2 to the x equals 0. This was actually the zero product property that told us that. And x squared minus 1 equals 0. This is actually impossible because, to get the x out of the exponent, I would take an ln of both sides. But what's the ln of 0? Undefined. So this produces no solution. But this one will get me two solutions. X squared equal 1, square root both sides. X equals plus or minus 1. And those would be my two answers. How about this one? This is something I would never give you guys on a test, but I might give you on some homework. Exercise 40, we have e to the x minus 12 e to the negative x minus 1 equals 0. So how do I solve this? Well, first off, you need to realize this is e to the x minus 12 over e to the x minus 1. So this has some of my variables in the denominator. So the first thing I want to do is clear the fraction. So I multiply everything times e to the x. So that'll get me e to the x squared minus, well, let's do this term first, minus e to the x, and then minus 12. Oh, I forgot the x. Equals 0. Now, this is quadratic in form. You may not recognize it, but we have a squared term, we have just a straight term, we have a constant. So you can treat it like as if it were just a quadratic equation. So if I had m equals e to the x, I would have m squared minus m minus 12 equals 0. So I could factor it to, let's see, m minus 4 m plus 3 so that means I have m equals 4, or m equals negative 3. So that means e to the x equals 4, or e to the x equals negative 3. And then to get the x out of the exponent, you would take an ln of both sides, and this would be a very good pick of an ln, because ln and e, remember ln is log base e, will just cancel out. So that would just be x equals ln of 4. And if we do the same thing on the e to the x equal negative 3, we will get x equal ln of negative 3, but ln of negative 3 is undefined, so that's not going to work for us. Alright, I think we will end the first video here, and we'll actually come back and do a second one for 4-5 to do logarithmic equations. See you then.